Hello, my name is Josh Oberg, and I'm a GIS analyst with the ACPF National Hub. In this video, we're going to discuss the More Terrain Derivatives tool. This is the fourth tool in the Precision Conservation Siting Practices section of the ACPF Toolbox. Ian Moore developed several secondary topographic attributes. Secondary topographic attributes combine two or more primary attributes, and primary attributes consist of derivatives from an input DEM, such as slope, flow accumulation, curvature, or upslope contributing area. But by combining these primary attributes, our ability to understand the landscape characteristics that involve hydrology and geomorphology or ecology are greatly enhanced compared to what can be gained from looking at just a single attribute. The More Terrain Derivatives tool produces one primary attribute, and that's a specific catchment area, which is calculated using the d-infinity method. Unlike the d8 flow direction method, the d-infinity method is a more advanced flow writing algorithm. The d8 method routes water from one cell to only one neighboring cell, while the d-infinity approach, which was developed by David Tarbotten from Utah State University, allows flow to be proportioned from one cell to multiple downstream cells based on slope angle. This approach allows flow to diverge or converge, whatever the landscape is naturally telling it to do. Using the d-infinity method, a specific catchment area grid is generated, which is the contributing area per unit length. In our case, the length is the grid cell size of 1 meter. The More Terrain Derivatives tool also generates two secondary topographic attributes. The first being the stream power index, which is a measure of the erosive power of flowing water. This is found by taking the natural log of the product of the specific catchment area and the tangent of slope, and in this case, slope being beta. The second attribute is topographic wetness index, which predicts zones of saturation, where the specific catchment area is typically large and slope is small. This makes sense according to the equation, which is the natural log of specific catchment area divided by the tangent of beta. Again, beta is slope. If this is the first time that you're hearing about d-infinity or secondary derivatives, like the stream power index or topographic wetness index, or if you have heard of them before but aren't very comfortable with them, please do not use this as your only source of information. Feel free to go to any of the other sources listed on this slide to read further into them. It will really benefit you to understand how these work and how they should be interpreted, especially understanding them further than I'm going to go into in this video. When running the More Terrain Derivatives tool, a DEM is required, and it's up to the user whether you want to use a filled DEM or an unfilled DEM. If you use a filled DEM, that means that the sinks in the landscape have been filled, and therefore flow paths are going to go straight through depressions. This is going to result in higher flow accumulation values and therefore a higher stream power index. If you use an unfilled DEM, flow paths are going to end at each sink or depression, which therefore results in lower flow accumulation and a lower stream power index. These results are going to be used in later tools, such as the grass waterway siting. So depending on your landscape, if you know it has a lot of depressions or is very pocky, and that you won't site grass waterways through there, it may make more sense to use the unfilled DEM. However, if you're really unsure, the filled DEM is probably going to be your desired choice. As you'll see in later tools, you'll have the option to account for the presence of depressions, but it's completely your call. You could also run both and just use a different name in the outputs. Briefly, I just want to show the difference in results of the Grass Waterways tool when using an unfilled DEM versus a filled DEM. In this particular watershed, there are many depressions within the floodplain that runs through the center of the watershed. Using the unfilled DEM reduces the amount of grassed waterways because the stream power values will be much lower within that grid compared to when using a filled DEM. In ArcGIS Pro, we will open the catalog window in the right side of the screen if it isn't already open by clicking the Catalog tab. Expand our ACPF Toolbox and expand Precision Conservation Practice Siting. Double-click the More Terrain Derivatives tool. This tool has two inputs that it's asking for. The first is our DEM, which is, as we've discussed previously, can be the filled or unfilled DEM. For this run, we will use the filled DEM, and we can add that in the first drop-down, as it has already been added to our map. The second required input is our slope raster, which has been auto-populated. We're going to get three outputs of specific catchment area, the stream power index, and the topographic wetness index. These three outputs are automatically populated. Click Run to run the tool. The More Terrain Derivatives tool has just finished running, and we can see that the results are specific catchment area, stream power index, and topographic wetness index rasters have been added to our map. Let's take a brief look at our outputs. The specific catchment area is a measure of area per unit length. For us, that's 1 meter, which is the cell size of the DEM used to derive these results. We will do some symbolization so we can see a bit more. It's pretty bland at first, since it's similar to the flow accumulation raster. Select our specific catchment area in the table of contents on the left, and click the Symbology tab on the right panel to open the Symbology window. We will change the primary symbology to Classify. We will change the classes to 2, and then we will change the method to Manual Interval. For the first color, we will actually choose No Color. And for the second color, click on it, go to Color Properties. We will actually just make this a darker red. For the upper value of our No Color, we will double click in the cell and change it to 4,000. We're changing it to 4,000 because it's roughly 4,000 square meters to 1 acre. We can start to see these areas that have at least the 1 acre concentrated flow. If we look at it with our hill shade underneath, we can see it does make sense where these areas are. The next output is stream power index. Already we can see there's a lot of detail to this raster, but we will add some color to it as well. Click on it in the table of contents to activate it in the Symbology window. We'll change the color scheme to yellow, green, blue, continuous. And then we'll change the statistics to DRA. We can really start to see where flows are converging and diverging. As the areas get darker, this is where we have high erosive power, and it makes sense that this does coincide with our stream reach. Now let's take a look at our topographic wetness index. Select it in the table of contents, and we're going to change the symbology to yellow, orange, brown continuous. With this color scheme, areas that are into the darker reds and browns are areas of saturation. This makes sense, as we can see our wide river is in the darker colors. Here, the specific catchment area value is high, but the slope is lower, and this results in the slower moving flow, allowing it to saturate an area. To recap, we ran the More Terrain Derivatives tool and discussed how these could be used to assist in conservation practice siting. In the next video, we will run the next precision conservation practice siting tool, grassed waterways.